All right, we're gonna go ahead and get started. Hello, good morning, good afternoon, good evening, whenever you're watching this. Hopefully, first off, I hope you guys all had a great weekend. Hopefully, you got a little bit of extra rest with this daylight savings time that happened yesterday. So hopefully, you got that last good hour of rest. We're gonna get started today with lesson three, but before I do that, I do have a couple of announcements. And these announcements I'll also post in an email that I'll send to you and your parents as well. So first off, this week we're going to go over lessons three and four. Now, I noticed that when I was checking the data for lessons one and two, some of us may have not finished the exit tickets from last week. So what I did was I reopened those if you did not finish them, and you're going to have until Friday at midnight to get it done. So, pretty much by the end of this week, the expectation is that you'll have the exit tickets for the first four lessons. So, the two from last week and then the two from this week. You should have all of those completed on Illuminate by 11:59 on Friday night. So, please make sure that you get that done if you haven't yet. Second thing, on Tuesday, which is, I believe, the 4th, it is an asynchronous day. So although I will not see, or although my B-day classes, you will not be in school that day, the expectation for you all is still to be able to look at these videos and complete the exit tickets because they're on Blackboard and because you can see these videos on YouTube. There should be no reason why you can't access it. Okay. And if not, then when you return on Thursday, expectations still stand. You have until the end of the week to get those exit tickets completed if you have not done so. All right. So, again, I will post all of these in Blackboard. I'll post them in an email sent to you through Parent Square as well. But I just wanted to say that before we get started. So, that being said, we're going to start today on page 10 of our Unit 3 packet, and we're going to start with Lesson 3. All right, so lesson three, we're going to just be practicing with exponential functions with what we've been dealing with last week. So pretty much the goal for this week is you're still going to be able to create these types of functions from tables and graphs, but also we're going to be looking at characteristics of exponential functions. All right, so we're going to be looking at still like domain and range, but we're going to be introducing a couple of new parts to our graphs as well, so that way we know exactly what it is that we're looking for. But before we get into today's lesson, I wanted to at least give us a little recap or refresher on what we have dealt with so far. And so to help us with that, we do have a do now for this lesson. So the do now, it gives you a scenario. It says that we're looking at a swimming pool and the bacteria count in the swimming pool starts at 1500. And this is on Monday morning at 8 a.m. And then what this tells us is that the count or the number of bacteria, it doubles every day or basically every 24 hours thereafter. So what we want to do is that we want to create a function representing the scenario. So we need to figure out what's our initial value and our growth rate. Then we want to write our equation using this information. And then number three is asking us to figure out how much bacteria we would have after 3.25 days afterwards. Okay, so take this time, maybe take about 4 minutes to answer questions one, two, and three of the do now. And then afterwards, we'll focus on questions four and five. So I'm going to go ahead and pause it. And when you unpause it, you're going to see the answers for those three questions. All right, so we are back. So looking at the first three questions of our do now, all right, based on the scenario that we're giving in our do now, your initial value, well, what we started off with in terms of bacteria is 1500, and our growth rate is going to be 2. Why? Because the problem tells us that the count doubles every day. So that's why the growth rate is 2. Now, for the question number two here, we had to write a function that represents the scenario. So if you remember from lesson one of unit three, we looked at how we can write a general equation for an exponential function, which is this here. we said y is equal to a times b to the x power, where a represents our initial value, or in other words, our y-intercept, and b represents our growth rate. So since our initial value here is 1500 and our growth rate is 2, we can rewrite this equation as y equals 1500 times 2 to the x power. So that is going to be our function for this do now. And now for question three, what we're doing is that we're taking how many days that are given to us, which is this 3.25, and we're going to plug that in for x. So if we take this equation, we're going to do 1500 times 2 to the power of 3.25. And so if you plug that into your calculator as it is, then what we should get is 14,270. That is going to be our bacteria count after this many days have expired. Now, what we talked about in lesson 2 from last week is we introduced another equation. This is for what we called continuously compounded interest. All right, so if you remember that formula, the formula that we had was APERT, where we had A is equal to P times E to the power of R times T. Now remember, each of these variables here represents something. And if you don't remember, okay, remember A here represents our final amount. P in this case, it stands for principal, but principal in this case is a fancy word for your initial value. So P is our initial value. E, if you remember, this is a special number. This is called Euler's number. And if you remember, Euler's number is something like 2.71828, so on and so forth. All right. But usually our calculators that we use recognize E as its own number. And so you can just use that. All right. So then continuing with this, R represents our rate and T represents time. So that's what everything from this formula here represents. And so now that we have this equation that we also introduced, question 5 at the bottom here is asking us, could we use this formula to find the answer for number 3? So in other words, can we use this formula here and still get the same value of 14,270? Now, if we were trying to use this formula, let's think to ourselves, okay, well, we're trying to find A because we're trying to find the final amount. All right. So we're trying to figure that part out. Now, P, which is our initial value, well, we have that. That's 1500. Okay, so in our sense, we might think, hey, okay, P is equal to 1500. Now we know Euler's number, no biggie. We know the time because the time is 3.25 days. That's how much time expired. The thing is, we do not have a growth rate. We don't know this information. Well, you might be thinking, well, isn't the growth rate 2 because we said that it doubles every day? Yes, technically speaking, that is true. However, we want to be careful because the key for this is that our growth rate is continuous, meaning that it is happening every second of every minute of every hour of every single day. The thing is, with this type of problem, all we just know is that each day after each day expires, the growth rate doubles. It's not a continuous growth rate, it just happens sporadically at the end of a certain time frame expiring. So, because of that mindset or because of that reasoning, unfortunately, we cannot use this. So, we cannot use this formula for that reason. So because we're not dealing with something that is growing continuously, meaning, like I said before, every second of every hour and so on and so forth, that is why we cannot use this formula for number 4 here to get to the same answer. In fact, if we try to use this same formula or if we tried to use this, we're going to get a completely different answer altogether. And so that is something that we just want to be careful about, especially moving forward, when we are trying to identify which of these formulas are we going to use. Typically, when especially like the assessment down the road, you're not going to have to make that choice because we're going to tell you straightforward if you're going to have to use this formula here for number two, or if you're going to have to use this formula here for number four. So don't worry about if you have to choose between the two. We will tell you that in advance. Okay, so that is their do now. That's kind of like what we covered from last week. So we're still going to be somewhat looking at this as well in lesson three. And so now what we're going to do is that we're going to move forward and move to page 11. So I'm going to go ahead and do that now at this time. Okay, so page 11, what we first want to do is just talk about identifying exponential behavior. All right. So, in lesson one of last week, we talked about two types of equations or functions. We talked about linear functions and we talked about exponential functions. And we talked about differences between the two. But the main thing or the main difference between linear and exponential functions is that for linear functions, they have a constant they have a constant rate of change. All right. So what we mean by constant rate of change is that as our x values get bigger, what we notice is that our y values, they're either going to be going up or be going down by a certain number. Basically, we're either going to be adding or subtracting a number each time, and that's going to be constant. All right, that is not going to be the same though for exponential functions. Instead, they have what we call a constant growth rate. And so what we mean by constant growth rate is that what happens to your y values is that they're either going to be either constantly multiplied or divided by some number. So what we want to look for, especially if we're given a table, is that we really want to focus on our y values and we want to see what is happening with them. If we see that our y values are going up or going down by some number like being added or subtracted to it, that should tell us that we have a linear function. But if we notice that our y values are being constantly multiplied or divided by some number, that is going to tell us that we have an exponential function. All right, so how we're going to look at this, we have four tables listed here. We're going to do one problem together, but the goal is that we're going to look at each of these four tables, and we're just trying to identify, based on this, if we have a linear function that we're dealing with, or if we have an exponential function. So let's look at part A. So looking at part A, we see our x values here, and our x values are just being added up by 5 every time. Okay, nothing biggie. But again, the key for us is to look at our y values. That will indicate for us what type of function it is that we're dealing with. All right, so if we go down the line here, we go from 64 to 32 to 16 to 8 to 4 and to 2. So from 64 to 32 and from 32 to 16, you might say to yourself, okay, this is being cut in half every single time. Or in other words, what's happening here is that I'm dividing each of my y values by 2. So because I'm constantly dividing my y values by 2, this should tell us that, okay, what I am dealing with here is that I am dealing with an exponential function. So going back up here, the question is asking us if we're dealing with an exponential function or if we're dealing with a linear function. And we need to write yes or no. So is this an exponential behavior? We're going to write yes. Okay. And the reason why this is an exponential function is that we have a constant growth rate where we are dividing by 2 every single time. All right, so that is the goal for what we're trying to do for the rest of these 3 tables. So take 5 minutes, look through part B, C, and D, identify if you're dealing with a linear function or an exponential function, and then by the time that you unpause this video, you're going to see the answers for each of these as well. So go ahead and pause your video now. All right, we are back. So looking at my answers here, so we already looked at part A. We said that this is an exponential function because we have a growth rate here where we're dividing our y values by 2. For part B, this is also an exponential function that we are dealing with because as you look at your y values here going down the line, you should notice that your growth rate here is happening where you're dividing each of these by 5. So nothing wrong here. This is an exponential function that we're dealing with. For part C and D, on the other hand, these 2 functions actually turn out to be linear functions because as you notice here for this y, for the y values here, you're noticing that they go up by 4 each and every single time. So you're adding 4 to your y values constantly. So that is why we are dealing with the linear function here. And then for part D, same idea. The only difference is that your constant rate of change here is that you're adding 2 to your y values every single time. All right. So again, if you're noticing that your y values are being added or subtracted by the same number every single time, that means that you're dealing with a linear function. But if you have a case like these two where you're multiplying or dividing by a number every single time to your y values, that tells us that we have an exponential function. All right. So that is how we identify it from a table. Now, going back to the function for exponential functions, this should look familiar because this is the general formula that we've been talking about. We had a times b to the power of x. But there might be times in which you might be adding or subtracting something behind that. All right, so this does here, this variable k, this does have a meaning. And so we're going to talk about it now. We already know that for exponential functions, a represents our initial value, or in other words, this here will be your y-intercept. All right, b represents your growth rate. All right, but k, on the other hand, k actually represents something that is called a vertical shift. Now, this will be important for us when we talk about graphs, but we're going to look at that in a moment. When it comes to exponential functions, though, your b value, aka your growth factor, is always a constant, so it's always a number, and it's never going to be equal to the number 1. The reason for that is because we already know that 1 raised to any power is just going to be 1, so there's no growth involved. It's just going to stay the same. All right, so 1 to the 5th power, 1 to the negative 57th power, 1 to any power is going to be 1. And so that's why we never really consider these types of problems with that growth factor. Now, if we notice that our growth factor here, or b, if it's bigger than 1, that means that what we're dealing with is an exponential growth problem. And if we notice that our value for b is less than 1, that means that the function that we're dealing with is an exponential decay problem or decay function. So in the last lesson, we did talk about exponential growth versus exponential decay, and we talked about that with the continuous compound formula. But if we're talking about a standard exponential function like this here, how we identify if it's a growth or decay model is really dependent on what our growth rate is going to be. And so if our growth rate we know is a number that's bigger than one, we have a growth model. If this number for b is less than one, that tells us that we have a decay function. So that's how we can tell the differences between the two. So now what we're going to do is that we're going to take this information, we're going to go to page 12. So I'm going to flip this page over. And now we're going to talk about still how this can affect us in terms of characteristics of our graph. So one characteristic of an exponential function that we have to deal with is something that is called a horizontal asymptote. What this is essentially like a barrier. It's like a do not cross line that our function will never go past in terms of when we graph it out. And so the horizontal asymptote, this will actually be equal to whatever our value for k is. That is why we care so much about that vertical shift, because that is going to tell us where this barrier is going to be located. And when we get to the graphs at the bottom of this page, I'll show you how that looks. But just make sure you guys have this written down in your notes. Now, when it comes to domain and range for exponential functions, all right, the neat thing, first off, is that if you're dealing with an exponential function, doesn't matter how it looks, the domain for it is always going to be the same. All right, the domain for exponential functions is always going to be all real numbers. As long as there's no limit in terms of what numbers we can plug into the function or depending on like the context of the problem, if you're just given a standard equation, your domain is automatically going to be all real numbers. All right. The range, on the other hand, might be a little bit different. It's not going to be all real numbers every single time, unfortunately. The range really depends on that vertical shift, what we identify as K from the last page. And this will actually tell us this horizontal asymptote. This is going to be helpful for us with identifying the range to our function as well. All right, so we have 6 problems in the middle of this page. We're going to do a couple together. And the goal for each of these problems is that we just want to identify some characteristics about it. We want to identify if we're dealing with the growth or decay model. We want to identify what the growth factor is. We want to figure out what is our y-intercept. And then we want to figure out if the function or where the function has a horizontal asymptote. Okay, so let's look at the first problem together here. So all we just have is y equals 5 to the power of x. Okay, now if we go back to the previous page in terms of looking at the formula that we had here, we had y equals a times b to the x plus k. Now looking at what we have for number one, all we just have is 5 to the power of x. So there's some things that might be missing. So we got to kind of fill in the gaps here. So I'm going to rewrite this equation to make it a little bit easier for us. All right, so first off, I'm going to leave 5 to the x. Now, this here, I'm going to put in parentheses because this here is going to be my b value. Note that I do not have an a value in front. If there is no a value in front here, automatically assume that it is the number 1. So in this case here, my a value is 1. Now, at the end of our function, notice that we're not adding or subtracting anything. So if I'm not adding or subtracting anything at the end of my function, assume that we are adding the number 0 to it. So in other words, we can rewrite this function as y equals 1 times 5 to the power of x plus 0. Now, looking at this function here that we're dealing with, this will be a little bit easier for us to identify these components that we had to fill in. So first off, are we dealing with a growth or decay model? So if you remember on the previous page, to identify that, we need to look at our growth factor, which is our B value, which in this case is 5. So I'm going to go ahead and just fill this in. This is 5. So since 5 here is a number that is bigger than 1, this tells us that we are dealing with a growth function here. All right. Now, the next part that we need to identify is our y-intercept. So again, if you remember on the previous page, if I go back, the y-intercept is the same thing as our initial value, which in this case is our value for a. So if we go back to number 1 here, our value for a here is 1. So if we want to write down our y-intercept, remember it's a point, just not a number. Our y-intercept in this case is going to be the point 0, 1. So that is our y-intercept. And then now the last thing we need to fill out is our horizontal asymptote. So if you go to the top of the page, we said how we write our answer for a horizontal asymptote. We just write y is equal to whatever our value for k is. In this case, our k value is 0. So that means that for a horizontal asymptote, we are going to write y equals 0. So these are all the components for this specific exponential function. We're going to do one more. We're going to look at number 2. So for number 2, same idea. This time we just have 0.5 times or 0.5 to the power of x. If I were to rewrite this, same idea as before, I don't have an initial value in front here, so I'm going to assume that it is the number 1. Then this is 0.5 to the power of x. And since I'm not adding or subtracting anything afterwards, I'm just going to write a plus 0. I'm going to assume that we're just adding 0 behind it. So now looking at what we wrote here, are we dealing with a growth or a decay model? In this case, we have a decay model. Why? Because if we look at our growth factor, the growth factor is 0.5. And this number is less than 1. Now, our y-intercept, again, we have to look at our value for a, which in this case is 1. So that means that our y-intercept in this problem is 0, 1. And then for our horizontal asymptote, we say it is y equals whatever our value for k is, which is the number that we're adding or subtracting at the end of our function. In this case, since we're adding 0, that means that our horizontal asymptote is y equals 0. All right, so we did the first 2 problems together. And so you're going to take the next, let's say 7 minutes, and you're going to do problems 3, 4, 5, and 6, where again, you're identifying all 4 components to each of these functions. So I want you to go ahead and pause this video, and then once you're done, go ahead and unpause it, and then the answers for each of these problems will be populated here for you to double check to see if you got right. So go ahead and pause your video now. All right, welcome back. So as you can see, I've gone ahead and filled in the answers for problems 3 through 6. So please take a moment to look through each of these answers here to make sure that you have the same thing as I wrote. And if you do not have the same thing, please make sure you reach out to me in terms of asking questions so that way you can get a better understanding of why each of these answers are what they are. All right, but for now, we're going to go ahead and move forward. So knowing these components for each of these problems listed here, what we want to do is that we want to take this information and we want to graph some of these functions. So if I want to graph some of these functions, we're going to look at the bottom of page 12 here. And for our problems here, I want to go ahead and graph number 3 for this one. And we're going to graph number 6. So we're looking at these 2 problems here on the right column. So I want to graph both of these 2 functions. Okay, no problem. So if we're going to graph both of these, We're going to do this in 3 steps. Okay. First step is that we just want to label our y-intercept, or we want to plot that. The second thing that we want to draw is our horizontal asymptote, which I abbreviate HA because I don't want to write the whole thing. And then the third thing that we're going to graph is basically if we're dealing with a growth model or if we're dealing with a decay model. Now, depending on what type of model it is that we're looking at, our graph is going to look different. If we are dealing with a growth model, that means that our graph is going to look like this. And if we're dealing with a decay model, what that means is that our graph is going to look like this. So if we're looking at number 3, okay, so let me go back up to number 3. The first thing we want to look at is our y-intercept, which we said the y-intercept is 0, comma 1/2. So, okay, this is my x-axis, this is my y-axis. Here's 1, so that means 1/2 is right in the middle. So this is my y-intercept that I'm labeling. That's my dot. Okay. Now the next thing that I need is my horizontal asymptote. Let me see if I can use a different marker for this so that way you can kind of see it a little bit better. Let me pull one out right quick. Give me 1 second. All right, in this case though, as I'm grabbing some markers so that way you can see this a little bit better. If we go back up to number 3, it says here that our horizontal asymptote is located at y equals 0. So I'm going to use let's use a green marker. Why not? Because my last name is green and my favorite color is green. Don't judge. All right. So if our horizontal asymptote is at y equals 0, that means that our horizontal asymptote is literally going to be the x-axis. So I'm going to draw a dotted line here to represent that. And again, this line that I drew, this is like a do not cross barrier. So when you're drawing your graph, what's going to happen, since, by the way, if we're going to draw our curve, we got to make sure that we check for if we're dealing with a growth or a decay model, which for number 3, we're dealing with the growth. So that tells us that our graph is going to look like this curve here. So what that means is that our curve, we're going to draw this same exact curve. It has to go through this point here. And on top of that, it is not going to cross this green line that I made, because that is our do not cross barrier. So what that means is that our graph for this function is going to look something like this. Now, is it precise? No, but at least you have an idea of what the graph should look like based on the information that we filled out. Okay, so now we're going to do the same thing for number 6, following these 3 exact steps here. All right, first step, y-intercept. In this case here, for number 6, your y-intercept is 0, comma 1. So that means that I'm going to draw a dot right here. Okay. Next thing is my horizontal asymptote. This case here, it is located at the point, where is it? Oh, wait, time out. I make a video, and the crazy thing is that, yes, even in my videos, I make a mistake. All right. Now, where's my mistake? This is actually not going to be our y-intercept. Oh, I thought you said it was because the a value here is 1. True, but we have a vertical shift here of -4. So that does play a role here in terms of our y-intercept. What that means is that while normally, yes, it would be 0, comma 1, however, since we have this vertical shift of -4, that means that we have to move it down by 4. So in other words, if we bring it down by 4, 1, 2, 3, 4, that means that our y-intercept is going to be down here. which means that our y-intercept is technically speaking 0, comma, -3. Okay, so if you do have a vertical shift, or if you do have a value for k, what you have to do to your y-intercept is that you have to either add or subtract by that number as well, because, like I said, it's either going to bring your function up or it's going to bring your function down. In this case, we have to bring it down by 4. All right, so little adjustment, my bad on my part for that. Hey, if you want extra credit from my class, if you want extra credit for this, if you send me an email saying that you saw this mistake and saying that, hey, stop making mistakes, then I will give you some extra credit or something for that. Okay, so that tells me also that you watched the video. Anyway, moving forward. So this here is your y-intercept. Your horizontal asymptote is at y equals -4. So I'm going to go down to -4, which is down here, and I'm going to draw a dotted line here, which will tell us this is our do not cross line. So last thing, we have our y-intercept, we have our horizontal asymptote. Now we just got to draw our curve if it's based on a growth model or a decay model. For number 6 here, we have a decay model. So that means that our function is going to look like this curve here. So I'm going to draw that. It is going to pass through our y-intercept and is going to continue going down until it gets close and closer to our horizontal asymptote, but it should not cross it. And that is what our function should look like for number 6. All right, so that is how we can take characteristics of our functions, and that is how we can use that information to our benefit when it comes to graphing. So now what we're going to do is that we're going to take this, we're going to move to page 13. All right, now on page 13, this is where you're starting your independent practice, where we have a couple of problems. We have 2 on page 13, and you have 1 more that is on page 14. Now, for these problems here, it's similar to what we have done. We're just putting all the pieces together. All right, so all we're doing is we're just taking this information that we learned and we're just kind of continuing with where we left off. Now, we're going to do number 1 together so that way you have an idea of how to do number 2 and 3 on your own for homework. Now, for number 1, this is your function, 2 to the power of x plus 1. And so first things first, we're trying to identify if this is a growth or decay model. Now, similar to like what we did for the previous problems, it might be helpful for you to rewrite this so that way you have all information in front of you. Note that there is no initial value here in front. So if there's not one given to you, you can assume that it is, again, the number 1. So if this helps you, we can rewrite this as 1 times 2 to the power of x plus 1. Oh, you may not see that. Okay, here we go. So now dealing with this and what we see here at the top, we have a growth model that we are dealing with. The reason why is because our growth factor here is 2. Now, our y-intercept, normally it would be 0, comma 1. But remember what I just said before, because we have this plus 1 at the end of that, we need to add 1 to it. So that means that our y-intercept here is actually going to be 0, comma 2. All right. Now for our horizontal asymptote, that really depends on what our value for k is, which in this case is 1. So that means that our horizontal asymptote is equal to y equals 1. Now, for your domain, we already talked about domain and exponential functions on page 11, I believe. Or excuse me, page 12 on the last page. We said that for any exponential function, regardless of what it is and how it looks, the domain is always going to be all real numbers. Okay, so that is always going to be true. The range, on the other hand, that is going to be the thing that changes. All right, so our range is like an interval. We're going from one number to another. Now, how we figure out our range is that we start with whatever our horizontal asymptote is, which in this case is 1. That tells us that the lowest that our y value can get is 1. The highest that our y value can get is actually going to be infinity. So in this case here, the range, how we write it out, it always starts with whatever our horizontal asymptote is, and then it's just going to go off to infinity beyond that. So that is how we identify the range for each of our exponential functions. Now, in terms of graphing it, what you can do to help you is that we can fill in this table here on the side. So what I will do is that you can do this for the other two problems as well. Here are a couple of x values that you can plug in. So we're going to take these x values and we're going to plug them into our function and see what we get. And whatever we get, that is going to be our y value. So for example, if I plugged in -3 into this function here, what I would get is that I would get 1.125. If I plugged in -2, I would get 1.5, I believe. Nope, 1.25, excuse me. If I plugged in -1 into this function, that is when I would get 1.5. If I plugged in 0, well, we already did that. If I plugged in 0, I get 2. If I plugged in 1 into this function, I would get 3. If I plugged in 2, I would get 5. And if I plugged in 3, I would get 9. So if you want to plug these values for x into this function as well, be my guest. You should get these y values here that I wrote out here on this table. So now we're going to take all this information and we're going to graph it, okay, using the same steps as I did previously. So first step, your y-intercept, 0, 2. So that means that we have a point right here. Next step is that we have our horizontal asymptote, which is y equals 1. So that means that we have our dotted line going across right here. All right. And then lastly, in terms of our graph, we're trying to identify, well, if we have a growth or decay model, because that tells us how our curve is going to look. Since we have a growth model, that means that our function is going to look, our curve is going to look something like this motion here. Okay. Now, if you want your curve to be a little bit more precise, this is where having this table here will be beneficial for us because we can plot these points on here so that way we can get a little bit more of an accurate graph. Now, if you want to, I leave that up to you to decide, but in this case, I'm going to do it just for us. So I'm going to just plug in a couple of the points that I can. So I have the point 1 comma 3. So if I go across 1, I'm going to go up 3. So we're going to have a point here. We're going to have a point at 2, 5. So we're going to have a point here. We're going to have a point at 3, 9, which is going across 3 all the way up here to 9. Okay. Now, if I want to just, stop here and then just kind of create my curve that passes through these 4 points that I drew out here, you're more than welcome to do that. So I'm going to go ahead and do that at this time. So that means that my function should look something like this. Okay. And then I'm done with that problem. So hopefully it's not too bad. All right. Because once you have identified all the parts or all the components to your exponential function, the graph is really not that hard. Because once you know the y-intercept, once you know where your horizontal asymptote is, and once you know if you're dealing with a growth or a decay model, then you already have a clear idea of what the graph should look like. So as long as you draw um like a good representation of the graph, especially if you're given like a problem like this on the assessment down the road. As long as you identify those important pieces like the horizontal asymptote, the y-intercept, and the curve in terms of like which direction it should go, then you would get full credit for it. All right, so that is how we deal with these problems. So we already did number one of the independent practice here together. So that means that you have two more. You have the one here for number two, and then you have number three that is on the back of this page on page 14. Okay, so you're going to do the exact same thing, similar to what I did. All right, and then once you have finished the remaining two problems, you are done with lesson three altogether. All right, and then the last thing you would have beyond that is the exit ticket that is on Illuminate. Now, similar to what we did last week with lessons one and two, depending on what day you have Algebra 2, there is a different code on Illuminate for each of the classes. I'm gonna pull it up right quick just to make sure I'm giving you the right information. So, in order to get to your exit ticket on Illuminate, you're gonna need the access code, or you're gonna need an access code. If you have me on A day, so again, if you have me periods one, three, or four, the code to access the exit ticket, it is FBDTWX8. So that is the code that you will use if you have me on B day. So if you have me periods 5, 6, or 7, the code that you will use is URR7M2W. Okay, so these are your codes in order to access the exit ticket on Illuminate. And like I said at the beginning of this video, both of these are going to be due at 11:59 on Friday. On Friday, I believe the date for that is the 7th. Okay, so you have literally the entire week to get that done. All right, so what's going to happen is that if you watch this video on Monday for my A days, that means that on Wednesday you're going to make sure we're going to make sure that you got these notes filled in for lesson three so you can get credit for that. And then on B days, we're going to check to make sure you have these notes completed uh, on Thursday, um, to make sure we can give you credit for completing the notes for this lesson. All right. So as always, these are the notes that you will need. But as always, especially when you get, oops, sorry, when you get to the exit ticket or when you get to working on the independent practice, if you do have any questions about this lesson or even with lessons one and two, please make sure you constantly reach out to me. If people have been texting me, and I would say that texting has been pretty easy in terms of getting a quicker response from me because I have my phone on me all the time. So if you do have questions, try texting me first and then email me afterwards if you just have like a general question. Otherwise, this is lesson three. Go ahead and get the exit ticket on Illuminate knocked out once you have finished the independent practice. And if you don't have any questions beyond this point, then I will see you for the next video uh, for lesson four. All right, have a good rest of your day, and I will see you next time.